Ever get this weird feeling like reality is stranger than we think? Today, we're diving deep into a theory that takes that feeling to a whole new level. The idea that our universe might just be one giant hologram. And to help us unpack this mind-bending concept, we're relying on this incredible article. It charts the entire history of this theory. Buckle up, because we're about to take a wild ride through black holes, quantum mechanics, and the very nature of reality itself. You ready? Let's go. So let's start, I guess, with the cosmic celebrities of the universe. Black holes. I mean, we've all seen the movies, right? They're like giant space vacuums.
They're fascinating objects.
Yeah.
For a long time, we thought black holes were, well, relatively simple. Just regions of extreme gravity where nothing, not even light, can escape. Imagine like a cosmic drain, where gravity is so intense that anything that crosses the event horizon, the point of no return, gets sucked in and can never get back out.
Okay, a cosmic drain. I can picture that, but it sounds like there's more to the story, right? I mean, they can't be just cosmic drains.
You're right. Back in the 1970s, physicist Jacob Bekenstein, he proposed this truly revolutionary idea. Black holes have entropy.
Now, entropy, I know that can be a bit of a head scratcher. It's not exactly a term we throw around every day.
True, it's not the easiest concept to grasp. Think of it this way. Entropy is like a measure of information messiness. Like a messy room has more entropy than a tidy one because there are more ways for things to be arranged randomly. Bekenstein, he realized that black holes, despite seeming like simple voids, must have a tremendous amount of internal messiness, a mind-boggling number of possible internal states.
So even though from the outside black holes seem simple, they're all the same, but on the inside they're incredibly complex.
Exactly. And this is where things get even more interesting. Stephen Hawking, he enters the picture and says, hold on, if black holes have entropy, they must also have a temperature. And if they have a temperature, well, they must be radiating some energy.
Wait, hold up. Black holes are radiating something. I thought nothing could escape a black hole.
That's what classical physics tells us. But Hawking, he took it a step further and considered quantum mechanics, the often weird physics that governs the very, very small. What he found was mind-blowing. Black holes actually emit a faint radiation due to quantum effects happening right at the edge of the event horizon.
Okay, this is blowing my mind a little bit. So black holes aren't actually completely black after all.
Precisely. They're more like very, very slowly evaporating cosmic drains. And this Hawking radiation, well, this means that black holes are slowly, over unimaginable timescales, losing mass. Theoretically, they could even completely evaporate.
Okay, this is where my brain starts to hurt a little.
Yeah.
Because if black holes can disappear, what happens to everything they swallowed, all that stuff, all that information? Did it have to go somewhere?
That's a very insightful question. This is where we stumble upon one of the biggest mysteries in physics, the information paradox.
So we've got these cosmic drains, and they're slowly evaporating. But where's all this stuff they swallowed going? It's like the ultimate magic trick. Now you see it, now you don't.
It's a truly perplexing puzzle. One of the fundamental principles of quantum mechanics is that information can't be destroyed.
So it's like even if you shred a document, the information is still technically out there, just, scattered into tiny pieces.
Precisely. But here's the catch. Einstein's theory of general relativity, the one that describes gravity and the large-scale structure of the universe, well, it seems to suggest that information can be lost forever inside a black hole. It's gone, down the cosmic drain, never to be seen again.
Wow, so we've got a clash of titans here. Quantum mechanics says information survives, general relativity says it's gone. I mean, what's a universe to do?
That's the crux of the information paradox. It highlights this deep incompatibility between two of our most successful physics theories. And it's not just a theoretical curiosity, It challenges our very understanding of reality. Because if information can be lost, does that mean the past is truly gone? Could it rewrite itself? These questions get really philosophical really fast.
Mind blown. Again. So if information isn't just vanishing into thin air, where does it go? Is this where the holographic principle comes in?
You're on the right track. The holographic principle, it offers a potential solution to this paradox. It suggests that everything we experience in our three-dimensional universe, well, it might actually be a projection of information that's encoded on a distant two-dimensional surface.
Okay, hold on. You're saying our universe is like a giant hologram? Like those images on credit cards that look three-dimensional even though they're printed on a flat surface?
It's a similar concept, but on a cosmic scale. Imagine a movie projector. It takes a two-dimensional film reel and uses it to project a three-dimensional image on a screen. The holographic principle suggests that the universe might work in a similar way. with information encoded on a distant surface that's projecting the reality that we experience.
That's wild. So how did physicists even begin to develop this, like, mind-bending idea?
It started with a few key insights. Remember Jacob Bekenstein, the physicist who discovered that black holes have entropy? Well, he also proposed the Bekenstein bound, which states that there's a limit to how much information you can pack into a given region of space.
So there's like a universal information storage limit, like the universe has a max capacity hard drive.
Exactly. Then came physicist Gerard Houft, and he took this idea a step further. He suggested that at the most fundamental level, we might not actually need three spatial dimensions to describe reality. Perhaps all the information within a three-dimensional space could actually be encoded on its two-dimensional boundary.
It's like the universe is playing a cosmic game of Tetris, trying to fit an incredible amount of information into a much smaller space.
That's a great analogy. And this is where physicist Leonard Susskind enters the picture. He made this extraordinary leap to suggest that the holographic principle might apply not just to black holes, but to the entire universe.
Wow, talk about a paradigm shift. So instead of a 3D universe with information inside, we're talking about a 2D reality projecting our 3D experience. That's like saying the universe is, it's like this giant cosmic movie being projected from some distant higher dimensional film reel. But if that's the case, what does this projection even look like? I mean, how do we even begin to imagine a 2D surface holding all the information of our vast universe?
That's where things get really interesting. There's this concept called the ADS/CFP correspondence. And while it doesn't tell us if our universe is actually a hologram, it provides a mathematical framework for how the holographic principle could work. It's a powerful tool.
A powerful tool, you say. Tell me more.
The ADS-CFT correspondence, it's a mind-blowing realization in theoretical physics. It links these two, seemingly unrelated theories. A gravitational theory in this particular type of space-time called anti-de Sitter space, that's the ADS part, and a quantum field theory that, well, it lives on the boundary of that space, and that's the CFT part.
So it's saying that a theory about gravity, like in one dimension, could be equivalent to a theory about quantum particles in a lower dimension.
Exactly. And this isn't just some mathematical trickery. It's giving physicists a whole new way to study and understand both theories. Imagine, trying to solve this really difficult puzzle, and all of a sudden you find this completely different puzzle that's somehow linked to the first. Solving one might actually give you clues to solving the other.
That's incredible. So while it doesn't definitively prove we live in a hologram, it does offer like a working model for how the holographic principle could play out in a real physical system. What I find fascinating is that, if true, the information on that distant 2D surface isn't just like some abstract code, right? It's what our universe and everything in it is actually made of. But where does this leave us with those other mind-bending concepts you mentioned, like entanglement, entropy, and firewalls?
Ah, yes. Let's dive into those. Entanglement entropy, it's a measure of how entangled quantum objects are with each other. You see, in the quantum world, particles can become, well, they can become linked, even if they're, light years apart. Measuring the state of one, well, it instantly determines the state of the other, almost as if they're communicating faster than the speed of light.
It's like they have their own secret language, one that like transcends distance.
Precisely. And what's even more fascinating is that entanglement entropy might be directly related to the fabric of space-time itself. It's like the universe is woven together with these threads of quantum entanglement.
That is both beautiful and mind-boggling. Okay, now for the firewalls, because that doesn't sound nearly as pleasant as entangled universes.
This is where things get even more intense. The firewall paradox. It highlights a potential problem with our understanding of black holes. Remember how we talked about information being conserved? Well, some physicists believe that for this to be true, something dramatic must happen at the event horizon of a black hole.
So instead of a smooth, gradual transition as you cross the event horizon, you're saying there might be a more abrupt welcome?
In a way, yeah. The firewall paradox, it proposes that there might be a firewall at the event horizon, this region of intense energy that would, well, it would incinerate anything that falls in, basically.
So much for my black hole vacation plans. But seriously, why is this idea even being considered?
Because it gets at the heart of some fundamental inconsistencies in our current understanding of physics. You see, if firewalls exist, they challenge some of our core assumptions about black holes and the laws of physics as we know them. It could force us to rethink, the relationship between gravity, quantum mechanics, and the nature of information itself.
This whole deep dive has been an incredible journey. We've gone from the depths of black holes to the vast cosmic canvas of the holographic universe. It's enough to make anyone feel a little small, but also strangely connected to something, much grander than ourselves.
I agree. It highlights the immense power of human curiosity. The universe is a vast and mysterious place, and it's through our constant questioning and exploration that we unravel its secrets.
And speaking of unraveling secrets, we've only just scratched the surface of these mind-blowing concepts. If there's one thing this deep dive has shown us, it's that the universe, it loves to keep us guessing. So here's something to ponder as we wrap things up. If our universe is actually a holographic projection, is it the only one? Could there be a whole multiverse of holographic realities out there, each one a unique and awe-inspiring expression of some fundamental cosmic code? If you're as captivated by these big questions as I am, be sure to check out the show notes for a link to that amazing article we explored today. And until next time, keep looking up at the stars and never stop questioning the nature of reality itself.